Pavel has had quite the academic experience. After graduating from Michigan with a background in physics and math, he spent 1 year abroad in Oxford during that time, and a master's in physics from Perimeter before eventually making his way over to MIT to do his PhD work with Jeremy England, which is where Pavel and I first met, and I had the pleasure to interact and chat and argue over the whiteboard. Since finishing his PhD, he's done some traveling and has been doing a 1 year postdoc at MIT, where he finished up the work that he's going to be presenting to us today, which has made a big splash in the field. So it's very exciting to have him talk about it. He has recently decided to move on to industry. So if anyone has any insights or connections and is excited about this stuff, please reach out to Pavel and help him on his next phase. So with that, please take it away.
Cool. Can you hear me? Am I unmuted correctly? Okay.
Sorry, I forgot to mention the decorum for questions. Please put your questions in the chat. If I will monitor the chat. If it seems that it needs a clarification, I will interrupt, but otherwise we will open up discussions to the end, at which point I will either read your chat or you can unmute yourself and talk. Okay, sorry, thank you.
All right, thanks, Jordan. Nice to be back at Michigan, sort of. Yeah, so I want to tell you about this recent publication we had, which came out in Science magazine, so that was quite exciting. It's basically kind of my PhD thesis work, and then wrapping it up, putting in a nice kind of story and over this last year. It's kind of a, so we called it a predictive principle for self-organization and active collectives. And the tagline's low rattling, as hopefully I will explain. And basically what I'm hoping that this presentation can do is kind of give you a sense of maybe the core of this idea, and that it's a very simple idea that you can actually hopefully make some use of in your own work with complex systems, non-equilibrium systems that you like, basically. So hopefully I'll convey kind of the basic structure. So I'll start off with this quote that I really like. It's only a slight overstating the case to say that physics is the study of symmetry, from Philip Anderson and More is Different. So before expanding on how this relates, why am I talking about symmetries? I'll go through the outline, so I'll expand on this quote, and then I'll say that in contrast to physics, complex systems is the place where most symmetries are broken, and there's very few left, and the traditional approach to handling complex systems is kind of to rely on remnant local symmetries that remain after all the fundamental ones kind of are, the global ones, big ones are broken. The principle that I'm proposing is kind of the opposite of that. So we call it rattling, and it's basically to assume that there are no symmetries in the system, that it's a complete mess, and to look for kind of typical behaviors. To show all that, I'll go through a few examples, such as discrete Markov chains, non-uniform diffusion, so where you're diffusing with a kind of non-uniform diffusion coefficient. Then the main system that we've studied, and why this was a science publication, an experimental realization of a swarm robotic system that we worked together with a couple labs on. And also maybe I'll get to at the end the application of this principle to Witschek model of flocking, which is this like very most famous active matter system, right? And this is just kind of to show that, you know, if we're claiming a general principle for active matter, we should probably solve the most famous examples with that. So to move on. So why is physics the study of symmetries? And this is kind of, so if we think of Newton's laws, we can state them as momentum is conserved unless acted on by a force. And that's basically a statement of conservation of momentum, which comes from translation invariance, that my experiment done here and my experiment done somewhere else is going to give the same result. In Boltzmann distribution, we have a lot of interactions, a lot of complexity, a lot of randomness, but there's still a energy conservation, right? So the total energy is conserved, which comes from time translation invariance. So my experiment today and my experiment tomorrow should give the same results, right? In field theory, the very way to approach a lot of questions is from symmetries, and our kind of most fundamental understanding of what a particle even is basically that particle is a representation of a certain symmetry group. So it's kind of based on a symmetry. And I'd argue in general that for any science, science is kind of the study of symmetries and patterns in nature. So it's really fundamental to our approach to science. And in contrast to that, in complex systems, we often have very little symmetry. So it's complex systems are systems composed of many heterogeneous, interacting, autonomous parts that form a whole that has emergent properties that are very different from the parts. So if we think of collections of organisms like an ecosystem, right? No two organisms are exactly the same. So there isn't that symmetry. There isn't exactly time translation or time translation symmetry. And it's kind of hard to find what symmetries are there. Brain composed of a lot of neurons also has this feature. We can think of society, lots of people, crowd dynamics, traffics, maybe cities, and how they function as an emergent collective, and things like markets. So the sort of industry I might be end up going into. Yeah, and so the hallmark of this is that almost all symmetries are broken. So fundamentally, these systems are all made up of some fundamental physics particles, right? That do obey, the laws of physics at the fundamental level are based on certain symmetry structure. But once you have so many particles interacting on this relevant scale of these systems where they actually function, none of those fundamental symmetries really matter anymore. So the complex system I will now focus on is this robotic complex system of particles, which is kind of a messy experimental system. And what's nice about it being a robotic system is that it's kind of perfectly controllable. So we have a lot of flexibility for what to do with it, right? Unlike maybe a lot of colloidal active matter that is studied where control is kind of more difficult to achieve experimentally. Here we can do whatever we want with it. And this was in collaboration with the Georgia Tech Robo physics lab run by Dan Goldman, who first designed these little robot smarticles, which I'll explain in a little more on the next page. And then another lab at Northwestern picked up on their idea, and these guys are an engineering control theory lab. And they basically made a much nicer, kind of really polished version of these robots that were kind of live controlled by a radio through a computer, right? And had kind of perfect ability to manipulate them in arbitrary ways. So the experiments that took us like almost a year to do in the first lab took us about like 4 days to reproduce in the second lab. So that's quite nice. And so what are these robots? Basically, it's a little control box in the middle that communicates with the computer and has battery and motors. And the motors connect to these little flapper arms on the sides that can be kind of manipulated in an arbitrary way. And these flappers don't touch the ground when it's sitting like that. So if it moves the arms, then it cannot translate, right? So if the arms are moving, the smarticle stays in place. But if you put kind of several of them together, then they can exhibit complex dynamics because they can kind of push off of each other. So any dynamics that happens is only possible through interactions. And the point about this system is that traditional control theory kind of can't do anything with it because the dynamics here are basically chaotic because you see there's a lot of kind of hard surface interactions and a lot of corners, right? And so every corner basically constitutes a bifurcation that like tiny changes in initialization can get them to push on one side of the corner or on the other, giving kind of a bifurcation. And so there's sensitivity to initial conditions, which over a long time kind of builds up and makes the dynamics basically chaotic, not predictable. So really modeling it as a microscopic system based on all the details is basically unhelpful for trying to control the collective, right? So traditional control theory methods can't get can't allow us to really get the swarm to do a particular task, if that's kind of what we want. And so instead of that, we are going to rely on self-organization. So so basically how the arms move, I can control externally through a computer, right? So one thing I can do is I can get the arms to move randomly, which is what I'm doing here. And then the dynamics are kind of exploring the space of possible configurations. So if I plot how the arms move, so this is the kind of input drive that I'm externally, exogenously specifying. These are arm angles for the three smarticles, and red and blue are kind of the left and the right arm. And so here they're moving randomly. You can kind of see that there's no correlation in how they're moving. And in this case, the system is just exploring all possible states. On the other hand, so this theory that I'll tell you about, which when I first came to work with this lab, was kind of in its nascent stages. It says that self-organization is only possible when the drive is predictable. And maybe you can even think of self-organization as the system kind of learning to predict its drive. And so when I first came to that lab, I kind of had the idea that if we wanted to see some self-organization or structured motion in these robots, maybe we should try driving them with something more orderly or something that is predictable, that has a pattern. So we tried controlling the arms in this particular way. And we saw that they very quickly self-organize into these sorts of patterns. You can see that there is repeatability, that they're stable there. And then sometimes they kind of stochastically transition to another stable pattern that is, again, kind of, you can think of it as like a collective orchestrated dance of these, right? So you can see that there's this kind of rotational symmetry, that they're in this triangle shape right now. And then they again stochastically kind of, there's a little bit of chaotic motion for a bit, and then they again settle into another self-organized motion pattern. And so this kind of happens. So we saw that there is self-organization. And basically, it's in terms of, in the context of this control problem that I was saying, that these guys aren't controllable using traditional control theory. Basically, this shows that the smarticles kind of spontaneously find coordinated collective behavior. And all we need to do is just to drive them with some structured signal. So give them external signal that they can self-organize. And a note that this didn't have to happen. So if we modify the system slightly by reducing the friction between the stage and the robots, but move the arms in the same way, then there is no self-organization. So here we put them on top of little beads that are very light, and they roll around, so they just give rolling friction, so they're like skating. So it's the same system, the arms are moving the same way, but now there is no self-organization, right? So the fact that they do find these very fine-tuned patterns is kind of a surprising and perhaps, unlikely example of fine-tuning, spontaneous fine-tuning. Okay, so in the context of robots and control theory, once they do find these coordinated collective behaviors, we can then kind of harness them for various task capabilities. So for example, we can get them to rotate the ring clockwise. So this is in one of these regular patterns. And the ring
Is he frozen for everybody?
Yeah. Yes.
I was going to ask the same thing.
Pavel, I think you might have froze.
just gets basically rotated almost deterministically. Then it will rotate in the opposite direction.
So
all the experiments I'll be showing. Yeah.
30 seconds we missed. You froze.
Yeah,
At least 30
Okay.
seconds.
go back
right
to
when
the
that first-
CW rotation.
Yeah. So let me just replay some of the videos. So in one of the kind of coordinated collective behavior, I can get the ring to rotate clockwise. And in another one of these attractors, the ring would rotate counterclockwise, right? So by controlling which coordinated dance these smarticles are doing, I can control which way the ring rotates, right? Also, most of the experiments I'll be showing are done when the ring is glued down. Here, the ring is obviously free to move, and you can see that it's rotating, but it's not translating anywhere. It's kind of staying in place. If I go to another attractor dance, then I can actually get locomotion, right? So here you can see it's in another state, and here it's kind of just slowly, but more or less deterministically translating, but without rotation in this case, right? So I can, by controlling these states, I can kind of control what, get these things to do tasks as a collective robot, as a robot made out of robots. Okay, so let's reflect a little bit on what I just went through. So basically, a complex robotic system self-organizes in the presence of a structured drive is what I was arguing. And now the question is kind of, can we understand, predict, and control the swarm as a collective machine by understanding how this is happening, right? And also, can we come up with kind of a general principle for why these self-organization is happening in the system, how to control it, and general that will, work for many complex systems, not just for this one. Okay, so moving on with that, in order to talk about general things, we're going to have to go quite abstract, kind of stepping back from this example of a robot swarm. And now I'm going to talk about a discrete Markov chain, very abstract dynamical system, basically where we have n discrete states that the system can be in, and n squared transition rates between them. So it's a random walker that is jumping between these, among these n states with these various transition rates. Now, if the system is in equilibrium, if it's an equilibrium system, then the rates will satisfy a detailed balance constraint written here. And in this case, the steady state probability of any given state can be given exactly in terms of the Boltzmann distribution, so in terms of the energy of that state. So there's this way to describe the steady state locally. If, on the other hand, I have a non-equilibrium system, then there are kind of, I'm talking about no constraints. And if there are no constraints, then I kind of know nothing about the system. So if I know nothing, then I can't really predict anything. And so this is kind of the situation of this quote from Ulam, using a term like nonlinear sciences, like referring to the bulk of zoology as the study of non-elephant animals. And so here we're talking about, a very broad set of systems. And so it's unclear, like, how could you ever predict something about, everything? But if we look at ensembles of these systems, so not a specific realization, but rather an ensemble, then we have a little bit of a different symmetry structure. So in the ensemble of equilibrium systems, we basically have n degrees of freedom because of the constraint of detailed balance. There's only n free things, so energy of each state you can vary, nothing else you can. And so each member of this ensemble satisfies the Boltzmann distribution exactly. Ensemble of non-equilibrium systems has n squared degrees of freedom, so all the rates I can vary arbitrarily as I want. And so here I can talk about a typical member of this ensemble. And a typical member can be studied by just choosing all the rates to be random, right? So if n is large, then a particular realization of a large n kind of Markov chain with all the rates chosen randomly is going to be fairly representative of all the possible Markov chains like that, because anything that doesn't look like randomness will require a lot of fine tuning in this case. Okay, so I'm looking at this kind of ensemble of non-equilibrium systems now, and now the problem is kind of very well defined, right? So now I can study this typical non-equilibrium system, which is just a random Markov chain with all the rates being independent, identically distributed random numbers. And I can similarly, as in the Boltzmann case, in the equilibrium case, I can study what is the steady state at a given node, steady state probability. In particular, maybe I can try to express it in terms of some local observable, right? And very intuitively, it seems that one local observable that should be, at least correlated with the steady state probability is just the exit rate. And basically, the configurations that have a very low exit rate will, on average, tend to have kind of a larger steady state probability, right? That doesn't seem too surprising. From this, I can actually, in this case of random Markov chain, I can actually write this more precise equation that the steady state will be the inverse of the exit rate. And if I test this in a numerically kind of generated Markov chain of 1,000 nodes, then I can see that indeed the exit rate and the steady state probability are very well correlated. Okay, so this is cool. It's not surprising. It doesn't give an exact prediction for what the steady state probability will be. You could break it if you try to fine tune some of the rates in a particular adversarial way. But for a typical non-equilibrium system, there should be a correlation. And basically, this just very simple rule of thumb that you end up in places that you don't leave is what I will be in this work, basically what we just tried to formalize and make more precise and really understand when it does work, when it doesn't work. And ultimately, the statement isn't an exact prediction, but it does contain information. It's informative, and we can leverage that information to make predictions and to control complex systems where nothing else really works, right? So on average, it'll be kind of useful, is what I'll try to show. And this is basically this very simple rule of thumb is what maybe I'm hoping that you can get out of this talk that you can actually apply in some of your systems, because it's kind of very intuitive and very easy to remember. Okay, so let's see. So let's apply this to the robots, right? So we had this random drive where all the arms are moving randomly and can be plotted kind of in this particular way. And in this case, the exit rate of any given configuration is roughly the same as for any other configuration. And so I tend to just, in the steady state, I just tend to explore all sets of configurations fairly uniform. So that here I'm plotting sampled the various steady state configurations that in experiment the system tends to end up in. The full configuration space of the system is 9-dimensional, so x, y, and orientation theta of the body of each robot. And the arms, I'm only comparing configurations where the arms are all in U shapes. So it's kind of a Poincare section. So the arms are exogenously controlled, so I'm not considering them part of the configuration space. Okay, and here this is some 3-dimensional projection of that 9D configuration space, just to give a sense of what things look like. Okay, so here I'm just exploring configurations. If on the and this is, I can also, for every configuration, I can plot by color the exit rates. And so here you can see that there is a slight variation in what the exit rates for configurations is, but it's not too strong. They're all kind of the same color, roughly. If I now have a structured drive, if there is very kind of precise, predictable structure in the drive, then I get these very specific configurations that have almost 0 exit rate. So if I initialize my system in that configuration, then I don't really leave, right? So for example, this one. And now what I can do is I can, in simulation, I can initialize my system in all possible configurations. And for each one, I can plot the exit rate. So some configurations will have a very low exit rate, here shown by blue, basically. And most configurations will have a high exit rate, right? So there will be these very precise pockets of low exit rate configurations. And you can see that it's not just one, right? So there is several pockets. So it means that there should be other configurations that are kind of stable under this drive. And so here's another one I can show in this video where the 3 of them are kind of back to back and they're all doing the same thing. And I can have one like this where the 2 outside ones are in the same orientation and the one in the middle is kind of opposite phase or flipped over. And so this is also stable, right? Under this particular drive.
Pavel,
Yep.
We've got a question from Charlie. He wants a reminder of what R of Q is.
Yeah, so here R of Q is what's going to be rattling. And this is here just the continuum version of exit rate. So for now, let's just think about it as the exit rates that I had in the previous slide.
Could you tell us how you actually measured it in the simulation?
Yes, I will a bit
Okay.
later on.
All
So
right.
yeah, for now, just think of it as exit rates and specifically how to, because it's a bit more of a technical detail. So I think the intuition of exit rates is gets the point across. Okay, and so here, if I plot the steady state, it aligns perfectly with these low exit rate configurations. So to make this quantitative, we can actually kind of plot, as in the previous slide, I had the plot of steady state for probability for any node versus the exit rate for that node. Here I can plot steady state density, steady state probability density for various configurations versus rattling for various configurations. And so as visually in these two plots, you can already see that the steady state tends to concentrate in these blue regions. Here this shows that indeed they are correlated kind of quantitatively. I can also make the same plot for this random drive above. And what I see is that the correlation is kind of still there. It's still in the same axis with the same scales. It's just that the range of possible exit rate values or rattling values is much smaller. So that means that your rattling landscape is kind of much flatter. And so there isn't as much fine tuning to these pockets of low rattling, basically. And so this is kind of how we think of it, that different drives produce a different rattling landscape that then produces different steady state distributions. Okay, so the message here is that ordered behaviors are spontaneously discovered because they have low exit rates. Kind of intuitive, but here it sort of gives the first, maybe not too precise at this point, not too clear, but a first explanation of why we're seeing this self-organization in this robust one. So we can recap again. I was talking about a Markov chain with random transition rates and also this robot swarm. And here I'm showing kind of the space of configurations for both of them. And then for both of them, I have this correlation between steady state probability and exit rate on the x-axis. So when I first saw this, I was kind of a bit ambivalent about what I thought about it, because on one hand, it seems maybe it's really cool that this is kind of a theory that allows control and understanding of self-organization by controlling the way the system is driven. On the other hand, it also seemed kind of trivial in some sense that maybe all we're seeing is that a system goes to dynamical attractors, right? A dynamical system goes to attractors, which is kind of an intuitive statement, right? Because attractors are places that have low exit rate. And so a system ends up in long time in attractors. That seems kind of obvious. We knew that. And that you end up in places that you don't leave almost seems like a trivial statement that has kind of almost no content, right? But as such simple kind of rules of thumb go, well, when we try to make them precise and formal, it turns out that it's wrong, right? The simple rule of thumb that you end up in places that you don't leave. And it's wrong because places that you don't leave is a local statement about the place. And where you end up is a global statement about the steady state of the system at long times, right? So these are qualitatively very different beats with very different information. And this is the Landauer blowtorch theorem slide. So in 75, Landauer wrote this paper basically giving a counterexample for why you could never express the non-equilibrium steady state in terms of a local quantity, any local quantity. And I think I won't go through the details of exactly what he showed, but this is basically the example. I can go through it later if someone wants. But he showed that a non-local interaction, so an interaction kind of far away in the system, can impact the steady state probability somewhere else, right? The intuition in the case of discrete state Markov chain is that I could construct such a Markov chain where there will be a certain state that has a very large exit rate, but this exit rate doesn't actually, deplete the probability at the state because all of the probability weight just kind of circles back in on it, right? So state with a high exit rate, that does not guarantee you that you'll have a low probability, right? And so the way that we kind of circumvent this no-go theorem from Landauer is by saying that we're not looking for a general non-equilibrium steady state, but we're looking at typical non-equilibrium systems. Typical in the sense that there is no kind of fine-tuned adversarial fine-tuning, basically. There's no structure or symmetry that is being put into to kind of break the relation we're looking for. And so it kind of has to be, in some sense, this random system. So these two examples basically won't work. And the other thing is that we're not trying to predict the non-equilibrium steady state exactly. We're just giving kind of an approximate prediction, right? So there's noise around this rule of thumb, right? The idea is that you end up in places you don't leave in systems where you don't know exactly how to predict them or how to treat them in other ways, right? So it's kind of the first way to approach it. And maybe one way kind of that I like to think about this approach is that if we have in physics kind of simple systems where we know full details about everything, right? So like this pendulum, right? Then we can think of the spectrum from very simple systems to systems that are so complex that they're basically just white noise, or there's just nothing is predictable. Everything is just unexpected. And so that's kind of the opposite extreme. And if reality lies, of course, somewhere in between these two, right? Because there is some structure and simplicity, but there's also some complexity. And what physics tries to do is it starts on the simple end of the spectrum, and it adds kind of perturbative complexity. It adds like weak interactions. Maybe it increases the number of components. And what our approach is trying to do is go from the opposite end. It starts with things being completely random, right? We kind of imagine having our kind of prior belief about a system that we know nothing about. If I'm given a system and it's completely complex and I know nothing about it, then my prior belief about it is that the steady state is just uniformly, basically, I don't know what will happen. That's the colloquial way to say it, but the more formal way to say I don't know is that my prior is uniform, my prior probability distribution. And now we're trying to do a little bit better than that. So if the system is so complex, can we, have a slightly more meaningful statement than I don't know, right? Okay, so now let's go a little bit more precise into how we actually define this rattling, or the continuum version of exit rates, basically. And to do that, we talked about random Markov chains, or Markov chains as discrete dynamical systems. So here we'll talk about continuous dynamical systems. So a continuous dynamical system is going to have some d-dimensional configuration space. And so this isn't fully general, but quite generally we'll have, it can be described in terms of some system of first-order differential equations on that configuration space, which means that we can basically write it as a certain flow field. So for any point in configuration space, it'll tend to move in a certain direction, and maybe there will be some noise, which I'm adding just kind of for generality. Now we can, again, as for discrete dynamical systems, we can think of this notion of a typical continuous non-equilibrium system, which can be given by a random flow field in this high-dimensional configuration space. So here I'm just giving a kind of two-dimensional example of a random flow field, which I just drew basically. And you can see that already here, it's not fully random, it's smooth. And smoothness is a bit of a constraint that we have, because if we're trying to study continuous non-equilibrium systems, then they kind of have to be smooth. If they have discrete jumps, then they're not really continuous. So that's kind of the first constraint. And this already kind of, now first we have constraints that there is d-dimensional space. We also have constraints on smoothness. So these are all things that are making it kind of less random. This is all structure we're introducing. But our principle that you end up in places with low exit rates will, as I'll show, will basically still hold in these cases. So, okay, so now we have this flow field, and we have the dynamics in this configuration space. We can compute in this simple example, we can compute the flow lines exactly and see what the dynamics are. So this is kind of how you would actually follow this. But instead of doing this exact calculation, which will be hard, we can approximate the dynamics by just Brownian diffusion in configuration space. This seems a bit of a kind of crazy approximation, perhaps, that we had this particular flow field dynamics of our complex dynamical system. And now I'm just throwing all of that away. I'm just saying, let's imagine a configuration that is just undergoing Brownian motion through its configuration space. But actually in the 90s, people studied systems with a random, basically, diffusion in random force fields. For a while, they were looking for anomalous diffusion in that case. And it turned out that to get anomalous diffusion was actually quite hard. You needed to have like very long range correlations and a lot of structure to your system, basically, especially if it's a high dimensional system, if the configuration space D dimension is large. And so in most cases, the dynamics through the space actually looks statistically just like diffusion. So this approximation is actually kind of reasonable. But in order to not throw the baby out with the bathwater, I do want to keep some information about the underlying system. And so here I will have this diffusion coefficient depend on the configuration, so that my Brownian motion isn't just uniform, but it'll be faster in some places and slower in other places. And this is going to be basically my equivalent of exit rates that I had in the discrete dynamics. Okay, so how do I approximate this diffusion coefficient? I take a bunch of nearby initial conditions. I look at where they flow, and that's going to give me kind of an estimate of, so for this point, it'll be kind of a large effective diffusion coefficient. For this other point, it'll be a smaller diffusion coefficient. For some points, it'll be almost zero, right? And so I can color this configuration space by the effective diffusion coefficient I measure. So I'll have some places where you leave very quickly. They have a very high exit rate or high rate of diffusion. And other places that you don't leave. They're more attractive, and the effective diffusion coefficient is very small there. And this is basically going to be rattling. So then I can, so to define rattling more precisely, I'll actually define it as a logarithm of this diffusion coefficient. I'll explain why log kind of a little bit later. For now, it's nice that it gives us the structure that is kind of familiar from the Boltzmann distribution, right? So we have the steady state probability expressed in terms of e to the minus rattling. And this e to the minus just comes from the fact that I just defined it as a log. Usually it would be 1 over. Okay, and so basically now I've dropped my full dynamical description of the system. I replaced it by diffusion in basically non-uniform diffusion and configuration space, non-uniform Brownian motion. And from that, I can arrive at the fact that the steady state probability density of any given configuration will be given by the simple local expression. And basically, I will end up in places of low rattling, of low effective diffusion coefficient, because it just takes me longer to leave them, right? And this roughly matches the exact dynamics picture, right? So if I look at this exact flow lines, they tend to concentrate in blue regions. Okay, so now this is all kind of abstract. Let's apply this to our robotic system. So this is in simulation. What I can do to measure rattling is I can start off with 5 very nearby initial conditions of the system, and I can just see how they evolve. So for a high rattling configuration, they will spread out very quickly, kind of like this. And for another configuration that is low rattling, they'll also, somewhat start to spread out, but any way that they spread out will be kind of corrected for. It'll be like, so it's a bit of a self-healing, maybe you could say, that it comes back to being clustered together. And so this, the way I'm defining rattling here is also related to local Lyapunov exponents, you could say, or other things. Okay, so what I showed last time is that for this particular drive that I am showing in these videos, I get these certain states that have low rattling and that have a high probability density at long times. But clearly, this will depend on the particular pattern that I am driving it with, on the pattern of arm motion, right? So if I move the arms, if I started in the same initial condition, but I moved the arms of the smarticles in a different way, then it may not be a low rattling state anymore under a different drive. So the low rattling configurations are kind of drive specific. So if I have a new drive that is structured, and I'll call this one drive A, here you can see that different smarticles now have a different pattern than how they move their arms. Under this drive, I get a new steady state distribution, right? I can have drive B, which is yet again a different drive, and it will lead to a new set of low rattling states and a new set of configurations that are selected at long times in the steady state. What I can now do is I can use this idea of rattling and low exit rates to control what the system does by creating this new drive that combines drive A and B by just switching back and forth between them. So I drive it for a little bit with A, then B, then A, and so on. And I switch randomly. And now the only way for you to have a low exit rate or to be stable under this combined drive is to be stable under both the constituent drives, right? This is a very obvious sort of statement once you're thinking about exit rates, right? But a priori, if you're given this complex robotic swarm and you're asked to control it to get it to be in certain states, it may be kind of confusing to think like, where do you even start, right? And so here, what you get the steady state under this mixed drive is going to be the intersection of the steady states under the two constituent drives, because yeah, the only way to have a low exit rate under the mixed drive is to have a low exit rate under both constituent drives. Okay, so this basically, we can verify this quantitatively because here I'm just showing a picture, and basically, yeah, there's a correlation between the true steady state, mixed drive steady state, and this predicted one under the overlap. And the point here is that basically we can control which configurations the system ends up in at long times by designing the drive in these ways. Basically, by designing the drive so that the only way for your system, for you to be stable under this drive, is to be in a configuration that you want, right? It gives a, usually the control theory kind of approaches systems bottom up. We try to understand the microscopic details of the system, and then we try to get the system to behave as we want by putting those microscopic details together in the right way. Here, it's kind of approaching control from the opposite direction, almost top down, right? We, from an evolutionary angle, you could say, that we design an environment in which the only configurations of the system that will be stable are the ones that I want, right? Basically, if I want to have animals that are resistant to colds, then I kind of set up a cold environment and I wait for a few million years for life to adapt to that environment, right? Or if I just go to the North Pole and I find the animals there. So this is a similar sort of intuition. I design the environment instead of designing the system. And this will only work as long as my system is complex enough to have to be adaptive and to have like a wide library of possible responses, of possible ways it can behave, so that the right ones can be selected over time. Okay, so that's kind of a big point. And what I'm trying to do with this previous slide and also this slide is to show that this very simple rule of thumb that you end up in places you don't leave, that seems kind of trivial maybe, can actually provide some non-trivial insights. It basically has informational content that you can then use to control and predict complex systems. So here I showed an example of controlling. Now I'm going to show an example of predicting, analytical predictions, because so I can't analytically predict what will the self-organization that these systems will go into, kind of from first principles, right? Because I do need to go in and measure which configurations have low exit rates. So from local measurements, I can initialize and I can watch the system for a short time. So that's kind of a local measurement. I can predict the long-term or global steady state, right? But I still have to do those local measurements. So here, I'll show that after I do these local measurements once, I can then predict how the rattling landscape and so the steady state distribution will change once I change something about the system, right? So I start measuring my rattling landscape, measuring my local response functions in all configurations, and then I can predict how this local response will change once I change something about my system. In particular, as I showed earlier in the presentation, if I reduce the friction, then I see that the self-organization is destroyed. So in experiment, we can realize this low friction by putting this on these little ball bearings. In simulation, I can tune the friction down kind of smoothly and continuously, and I can have kind of a quantitative measure of how the steady state distribution is affected by friction. So if I do that in simulation, what I see in these steady state probability versus rattling plots is that as the friction is lowered, my rattling basically increases, the range of rattling values increases or is reduced, the range of rattling is reduced, and so the rattling landscape kind of flattens out, right? So I can see that the very low rattling kind of ordered configurations, those organized configurations, their exit rate starts to kind of grow as I reduce friction, and so they sort of melt away. So here's the analytical prediction that I can then make for the steady state distribution. So at high friction, so here over Dent coefficient on the left side of this plot. So this is showing in the colored curves, I'm showing the steady state at 100 representative configurations of the system. And you can see that some configurations have a very high probability and some have very low probability, right? As I reduce the friction, basically all the different configurations start to have low probability. So this landscape kind of smoothens out, and melt the low rattling states or ordered states sort of melt away in this sense. And the black curves give the analytical prediction for how this relaxation is predicted to happen, right? Because once I know what the exit rate of a particular configuration is, I can then predict how that exit rate will change once I lower the friction. Analytically. There is kind of a little bit of tricks that, or assumptions that go into this, but they're fairly straightforward and they end up working as seen here. Right. So, okay. So what did we see with all this? Basically, we saw that this idea of you end up in places that you don't leave as kind of rule of thumb. It requires non-trivial assumptions. So it is a kind of non-trivial physical prediction because it doesn't work always, right? It's this kind of, in science, the trade-off between, saying very, a lot about a very specific system or very little about everything, right? And so here we're kind of, if we say something about everything, then we're saying nothing. So here we're not talking about everything. We are talking about certain class of systems that require certain non-trivial assumptions, and that allows us to say certain non-trivial things. And this class of systems is this typical non-equilibrium system. So these adversarially fine-tuned systems will not work. And then we kind of, so that this idea gives us power to predict and control complex systems, this class of complex systems. And yeah, I hope that at least at this very abstract kind of level of rule of thumb, this idea is simple and intuitive, and maybe you can find it useful somehow. Okay, so that's the main part of the results, kind of the meat and potatoes of the presentation. Now we can go to the dessert a bit, just to look at some cooler consequences, and this will be a little bit dependent on time. So for now, I think I have another, what, like 5 minutes? They can go through things.
Yeah, like 5 minutes.
Yeah, cool. Okay, so first one thing I kind of like to talk about with this, and this is getting a little bit more speculative, but that rattling could be seen as a theory of adaptation. So I mentioned this top-down control, and this is what it's going to go for. But the idea is that self-organization is only possible when the drive is predictable. That kind of makes sense. If I'm driving a system with something that has no structure and is random, there's no way I can get self-organization, right? On the other hand, here I'm also thinking of it as self-organization as a process, as sort of the system learning or acquiring information about its environment over time. And I'll try to illustrate why I think this intuition is perhaps kind of cool or useful. So if I'm moving all the arms of every robot randomly, as we already saw a few times, so this is this drive represented, I can think of predictive information of that system. So this is information about the past history of the drive that is useful for predicting the future as being 0 bits. So if I know all the past, I still can't say anything about what will happen because it's random. And in this case, the steady state distribution is kind of very uniformly distributed throughout the configuration. If I now have a different drive that has a little bit more structure, so now all the arms are moving randomly, but each smarticle is doing the same thing as all the other ones. So they're all kind of indistinguishable. So this is what this pattern looks like, right? So you can see that over time it's random, but across the smarticles it's the same. Now my predictive information from the past that I could learn that is useful for predicting the future is just that they're all the same. And I can quantify this roughly as 4 bits because one smarticle I cannot predict at all, but then the 2 arms of the 2 other smarticles, so 4 arms, I can predict based on knowing this one thing. So there is some predictive information, and this gives a little bit more structure to my steady state distribution. If I have an even more structured or ordered drive, so now this is the drive we saw a few times where they're doing this very specific pattern, and I can quantify the information, the predictive information in this drive as 12 bits because there is a kind of 4 time steps that 4 arm positions that are being repeated periodically over time. So these number of bits is, it's maybe not too precise here, and you could argue with them in some way, but I'm just trying to show that the amount of predictive information is going up in these drives. So now I have even more kind of fine tuning and structure in my steady state distribution. And if I make the drive even more complex, have even more predictive information, so now each smarticle is doing its own thing, but it's periodic, predictive, so kind of like drive A. Now this takes 18 bits, so the amount of information about the past that will be useful for predicting the future there's about 18 bits here. And now I have even smaller, even fewer configurations that are stable because, for example, these first 3 drives are permutation symmetric with respect to smarticles. So I can swap all the smarticles, they're all identical. And that's what gives this nice flower sort of symmetry in these steady state distributions. And here this flower symmetry is broken. So my steady state distribution is sort of reflecting the information in the drive, the structure of the drive. If the drive is not permutation symmetric, my steady state is not permutation symmetric. That makes sense, but I think this kind of is a more broader sentiment. I can also look at how these steady states develop from a uniformly random initial condition, distribution of initial conditions. So I start just initializing in all possible configurations, and I start driving them with these 4 drives. And I can see that the entropy of my distribution basically kind of goes down, meaning that the steady state, the probability distribution is gaining more and more information as it's being in the presence, under the influence of the drive. The probability distribution is becoming more and more informative, getting lower and lower entropy. And they settle down in the order that I showed them here, right? So the one with the most information has the lowest entropy at the end of the day. The one with the least is the top. So it's kind of the drive information imprints on the system structure over time. And another way to phrase that same thing is that the system adapts to the information in its environment. And this arises from, again, this very simple kind of rule of thumb principle, but now also with the additional component that exit rates of various states depend on the drive that you're subjecting the system to. And a very complicated drive will be it'll be more difficult to be stable in the presence of a more complicated drive. So fewer configurations will be stable under a complicated drive than a simple drive. So if you are, the biological analogy is if you are living in an environment that is very difficult to predict, then you really have to be very fine-tuned and very smart in order to be able to survive in such an environment, in order to be able to resist the corrosive kind of influences of it. But that's getting a bit speculative, perhaps. Kind of along these lines, rattling is also, and maybe this is a bit important to mention, rattling can be thought of as the entropy of force fluctuations. So I said that it's this like effective diffusion coefficient, but then I also take the log. So more precisely, it's the log of determinant of this correlation covariance matrix of these various trajectories. And this can be thought of as basically the entropy of these force fluctuations at that point. And so in that sense, this also has this kind of connection to information, right? That rattling is really connected to how well you can, how predictably you can respond to your environment. So if I, for example, start with this particular deterministic drive, then I'm in one of the regular states. But now I start to increase P, which is the probability of making a random arm movement. So here in 80% of the cases, it's still doing the predictable thing. But now in 30% of the cases, it's doing just some random thing. So the entropy of the drive is slowly being increased. And you can see that, obviously, eventually, when this P goes to 1, all the arms will be moving randomly, and I will have no regularity. So the entropy of the drive is becoming completely unpredictable. Its entropy is being maximized. So here I'm kind of tuning it up. And so now there's no adaptation, no regularity is possible now that probability of making a random move is 1. And basically, so here P goes up from left to right. So you can see the left column is 0% random, middle is 20% random, and right is totally random. And the top row basically shows the rattling landscape, right? So when the drive is fully random, then all configurations just have a high exit rate. When the drive is
So
fully...
Pavel, I'm going to ask you to kind of summarize it up in the next minute or two, okay?
Yeah.
Thanks.
Cool. Yeah, so I guess the point here is that, again, as I mentioned a few times, the rattling landscape kind of flattens out as I have a more random drive. And this, while the correlation from steady state to rattling kind of remains throughout these 3 plots, its range gets squeezed down. And so the really fine-tuned steady state becomes kind of impossible. These high probabilities get washed out. And this is also analytically predictable. So as I said, rattling is the entropy of force fluctuations. So as I'm increasing the entropy of the drive, rattling just follows exactly that entropy of the drive because of the low rattling state. Okay, so that's probably a good place to stop. I have a few more kind of fun things to mention, more speculative and applications to the Vichek model, which are also a bit of a newer thing. And I'll just end on this acknowledgement slide of everyone I've worked with, Jeremy's group, and the collaborators we had at various universities. Thanks.
Thank you. Awesome. That was a lot of fun. I'm going to open it up to questions. We already have one in the chat. Mitchell, would you like to ask it yourself?
Sure. I was just, can you hear me?
Yes.
Sure. So I was just, I thought, yeah, it's really fascinating that you can get so much out of just looking at the, like the diffusion term in this approximation to a dynamical system. But then I was just wondering what, like, it seems to me plausible that you could make an advection term approximation too. And then I was wondering what that would do if you've ever thought about that.
Advection term approximation. So you're saying like rather than approximating, can you explain what exactly how you have this in mind?
Well, yeah. I mean, if you have this local ball of trajectories and they move out, and so you're sort of measuring the local variance in where those trajectories go. You could also measure like the local mean change of where those trajectories go and get like an approximation of the dynamical system that not only tracks how much they bounce around, but also where they move in the phase space.
So, okay, there's kind of a two-part answer to this. So on one hand, if I'm in a complicated, messy dynamical system in high-dimensional space, and I'm leaving a particular point, so I start with many, nearly initialized initial conditions, and they're all leaving in one direction. That's probably not an accident, right? It's a rare thing to happen. And oftentimes what tends to happen is you're probably in an attractor and they'll just come back, right? So they're leaving and they'll probably circle back, but that's a bit of a vague intuition. The more perhaps accurate answer is that under this assumption of typicality, right, that typical non-equilibrium system that is high dimensional and messy, those two ways that what you're suggesting and what I'm doing are basically tend to be the same, right? That again, they will differ very rarely. Because it's kind of a rare thing for a bunch of trajectories to leave a place and still stay together in this random force field.
Okay.
Other questions? Charlie, you're muted.
I had to wave my hand first before I unmuted. It's a fascinating idea to look at things like total exit rates or total entrance rates, which are different things. But one thing I would say relative to Landauer is that, let's say the total entrance rate into a state is a non-local quantity because it depends upon what you rate from states far away. Of course, if you knew the equilibrium distribution, you'd know that the average rate in, average rate out are zero in steady state, in a steady state. But the rates themselves, that's a fascinating thing. And the first example you showed, where you had your random Markov chain, right? Which I presume was from simulations. It looked like an excellent correlation between the steady state probability and 1 over the sum of the exit rates. It looked, and that was a 1 over, I guess, with a specific. That's, I wonder, because of course you didn't go to 10 to the 23rd degrees of freedom in your calculations, but I wonder, is there a theorem lurking there for at least a pristine enough subset of systems? Yeah, so that curve looks like a law with some noise, because you only had how many states did you have in that calculation? 100, 1,000. Well, square root of 1,000 is 30. I mean, I don't know. And these are probabilities, and you only had a finite number of realizations. How many realizations of randomness?
Oh, this is just one. This is just a single,
oh, see, just one. Oh,
it's a single network of 1,000 nodes. Yeah.
Oh no, but now take an ensemble and ensemble average these things.
Yeah. So this is so there's different distributions that I can sample the random rates from. So rates are always independent, identically distributed. If I sample them all from like a 0 to 1 or some Gaussian, right, then what I will get is that the steady state is almost the same. So it's almost uniform over the states. And the first correction on top of that uniform thing, the first correction in 1 over n, right, is going to be that this 1 over exit rate.
Right. Well, okay. Of course, you don't want to take Gaussian rates. You want to take squares of Gaussians or something. They have to be non-negative. Non-negative numbers.
Oh yeah, sure, of course.
Yeah.
But if I'm taking this sort of kind of reasonable, then I have very, so it's very slight fluctuations about uniform probability.
I see. Yeah.
Here I'm taking log normal.
Yeah, that's a
log
fat
normal
tail.
distribution.
Fat tail.
Yeah, a fat tail. And so here it's kind of simple. Like the fact that they're correlated kind of makes a lot of sense because I can make this tail arbitrarily fat, which means there will be this one state that has an exit rate that is like orders of magnitude higher than all the other ones, right? And so you can see that here the steady state is distributed over whatever 15 orders of magnitude, right? And the rattling is also over the same, or the exit rates are also distributed over the same. And so here I get a, I can, by increasing the tail of the log normal distribution, I can get this to stretch out as far as I want, basically.
Right.
It's also interesting that in the case of log normal, the entrance rates no longer correlate. Exit rates are predictive of the steady state, but entrance rates are not.
Oh.
I'm not sure why. This is just from numerics. It's, it's like a 5 lines of code to check.
Interesting.
But, yeah.
Okay. Very interesting. Very provocative.
Yeah.
Thank you. So we've had a request to hear a little bit more about the relationship to the VCheck model.
Okay.
So you got your wish.
So, well, I don't know if it's a wish, but yeah, let's see. Okay, so in the previous slide before this, I was kind of trying to set up a parallel with the Boltzmann distribution, right? So we have this e to the minus beta u, and here we have e to the minus gamma r, where gamma is basically a fudge factor. Roughly same as in Boltzmann. It's also kind of temperature is, yeah. And so if we think of that parallel to Boltzmann distribution, if we try to take it seriously, then we can think of a free energy, right? So we can think of minus gamma rattling plus an entropy term, right? And we can now map that over configuration space. So VCheck model is model of flocking, where you have these little active spins that tend to align with their neighbors. And so over time, they tend to flock unless the noise is very large. It's a system. So here it's high dimensional. It's I think here I'm showing 100 active spins or so. So this would be a 300 dimensional configuration space, X, Y, and theta for each one. Now I will, I could plot the rattling landscape over this 300 dimensional configuration space, but instead I will coarse grain, and I will plot it in 2 dimensions, where the 2 coarse grain variables I choose is n, which is mean number of neighbors that each void has. So if it's a dense flock, then it has kind of each void has a lot of neighbors. And if they're all spread out, then each void just has one itself as a neighbor. And mean neighborhood polarization. So how well they're aligned with their neighbors. And so in that space, each NP corresponds to a set of microstates, right? Because I'm compressing, I'm coarse graining the full microscopic configuration space. And that volume of that set of microstates will give this entropy term. Basically, it's a degeneracy term for every configuration. It's fairly natural. Also, each microscopic configuration and each of these will have a certain exit rate, right, rattling value. And so now I can, over this 2-dimensional configuration space, I can plot a landscape. So I'll show this. So these colorful curves are contours of this free energy landscape, you could say, plotted in 2 dimensions. So again, the x-axis, horizontal x-axis is n, and y-axis is log of 1 minus p. So related to p. And colors is basically free energy. So the red lines, the peaks of this landscape are that which should have the highest steady state probability distribution. And now the black dots are kind of results of where simulations end up. So if I just initialize a bunch of random simulations and I run them for a long time, this is where they tend to end up in long times for various system parameters. So the system parameters are shown above. So temperature is T is the temperature kind of amount of fluctuations in these voids, and R is the neighborhood size. So if the neighborhood size is very large, everybody is everybody's neighbor, and so they all align very quickly. If neighborhood size is very small, then they don't feel each other. They don't talk to each other. So at very high temperature, I don't get very much flocking. So your average number of neighbors stays low, and that's what's predicted both by the analytics and the numerics. And so you can look at the other plots, and you can see that there isn't an exact agreement, but there's kind of a qualitative trend that is being reproduced. And I'm also reproducing accurately when they do or do not flock, right, in this case. So when the peak of this distribution is either at 0 neighbor size or 15 neighbor size. And the point of this is that this is kind of done from first principles. So with the Smarticle robots, I had to do some measurements, and based on measurements, predict some other things. Here, by having some general understanding of how this model works, so having played with it, I can kind of look at what the exit rates will be for various N and P flocks, right? And so it's not it's not directly based on equations, but it is from first principles in this sense. Yeah, and so here kind of analytically, kind of fully analytically, I can predict certain qualitative behaviors of the system.